I know.
3 o'clock. We are going to get started. All right, so today, thank you all for coming. We have a setup of 2 talks today. These 2 talks are by 2 of our new postdocs, just so you get a little chance to actually hear more about their research than the 5 minutes you may have heard at Astro Symposium. So here we'll have a couple of 20-ish minute talks, and then you'll have a chance to ask some questions. So starting off, we have Jake Miller.
All right. Hi, everyone. Oh, wait. Howdy.
Howdy.
Yeah, I had to do it once. Okay, sorry. All right. Hi, everyone. Yeah, I'm from Michigan. Just came to Texas. It's been great so far. If you saw my talk at the symposium a couple weeks ago, we saw the 5-minute version of this. Now I get a whole 20 minutes to talk to you guys. Understanding the regions around supermassive black holes at the centers of galaxies using small robotic observatories. All right, so just a brief overview of what I'll be talking about today. I'll first cover some basic background information, talk about what AGN are, why they're interesting, why they're cool, and how I specifically study them using robotic observatories. I'll then talk about 2 of the different papers I've been a part of, Marquardt 876, and then the 4 years of observing we've done with the Zawada Observatory and some of the conclusions we found from that study. So, without further ado, let's cover some background. So active galactic nuclei, or AGN, as I'll be calling them a lot in this talk, occur when material falls into a supermassive black hole, typically about a solar mass worth of material a year, and due to the conservation of angular momentum, will form an accretion disk. Something similar to what we think it looks like here. This is an artistic rendition of it. This is not an actual image. But as it's falling in, it will produce a bunch of radiation through magneto-hydrodynamical friction. And so we want to understand these processes. We want to understand how these supermassive black holes grow, but we can't just simply point a telescope at them and resolve them. They're far too compact, and everything with our telescopes as they are today, we can't resolve the vast majority of the regions around an accretion disk here. So we have to use indirect methods to understand these accretion disks. And so I use a method known as continuum reverberation mapping. This is very similar to sonar, if you're familiar with the concept, and sometimes it's called also echo mapping instead of reverberation mapping. But this is a little rendition I did of the inner regions of an AGN system. Right, we have the black hole at the center here, and above it we have an X-ray corona. This is where some gas interacts with photons from the disk and produces X-rays via Compton upscattering, right? What's important is that it's compact, and we believe it to be located pretty, a little bit above the black hole itself. What will happen is these X-rays will go out in all directions, and some of them will even come towards us here on Earth, but some of them will go into the disk. And so if our theories of disk accretion are correct, that means the disk is optically thick, meaning that the X-rays don't go through the disk. They are instead absorbed by it and then re-emitted as a different wavelength of light, depending on the temperature of the disk at that point. So you can kind of tell from my very masterfully done arrows here that you can, if you go closer to the inner region of the disk, you will get ultraviolet light. And as you move further out, you get the entire optical regime here. Now, this is an important prediction that arises from this, and that is that we should see, they should all be related to each other, right? So if we see a flare in the X-rays, then we should see a flare in the ultraviolet and then a flare in the optical. The difference, the time, there'll be a time delay between these signals though, based on how long it takes for the X-rays to go and hit the accretion disk. Because of this time delay though, we actually are able to measure how big the disk is by looking at the different wavelengths of light. So if it takes, for example, 3 days for the X-rays to go to the accretion disk and hit this region of the optical portion, then we know that the disk is 3 light days big, so to speak. And so let me go ahead and give you some quick math. I promise it's not anything too complex. These are some of the approximations and assumptions we make going into doing this reverberation. So first, if we measure time lag tau, typically that's a signal, between different wavelengths of light, that approximates the radius r of our accretion disk. And that's just from geometric arguments comes out to being approximately equal to the radius divided by the speed of light, c. Now, for the disk theory, right, we have a whole bunch of equations that describe how a disk should operate. This is from Shakura-Saniev disk theory, and it's a little too complicated for me to get into in this talk. But if you can take my word for it, and if you don't, I have a backup slide. I can show you the math. But it's that the temperature is related to radius to a minus 3/4 power, essentially saying that as you move further out in the disk, it gets colder, which makes sense. And then finally, if we assume the disk behaves like a black body, we get this relationship between the wavelength of light we're observing in and the temperature, and that they're inversely related to each other. We can combine all 3 of these equations together to get a new relationship between the time lag of light that we're measuring and the wavelength we're observing in. And that is that tau is proportional to lambda to the 4/3 power. And this is fantastic because we can actually test this prediction observationally. we can go measure in a bunch of different measure a bunch of different wavelengths and then see if the time lags increase with wavelength as expected here. So we go ahead and actually, I'm going to show you all today how to do it yourself. All right, so you can all go out, get your own telescope, I'm sure you all have one, and then do your own study like this. It's very awesome. So first things first, find an AGN. Maybe you have your favorite. I do. This is a really great one, NGC 7469. Really bright, really close object here. And so I've gone ahead and already done the observing for you ahead of time, kind of like a cooking show. I already did the work, fun fact. So what you want to do though is once you found your AGN, you then want to observe it in a bunch of different wavelengths for about several months if you want to do continuum reverberation. So in this case, it was about 3 months, a little longer. And so if you don't know how to separate filters, this is what we use with observations. We just put these on the telescope, and this allows us to get different wavelengths out, sort of isolate the wavelengths we want to observe. I use U, G, R, I, and Z. I don't use Y just for reasons. But anyway, we use these 5. And this allows us to see the entire optical continuum, more or less. So once you've done that, you then want to build light curves, right? So once you've done your observations, make light curves of them. So this is NGC 7469 as observed between 2020 and 2021. We have 5 plots here, one for each of our filters, U, G, R, I, and Z. The x-axis here is the time in days we're observing. So each data point here is 1 night of observation. And the y-axis here are the relative flux strength for each filter. And so I'm going to talk about the G-band specifically because it's typically our highest signal to noise observations here. And so you'll see that as we go over in time, NGC 7469 starts off relatively bright, and then it kind of arcs down here, hits a trough, and then kind of jumps back up and then goes back on its merry way. Now we want to try next to measure time lags between these different light curves, right? So you want to look for features in G and how long it takes for them to reappear in these other wavelengths. I'm just going to show you by eye. I kind of drew a line here showing where the very bottom of this little trough is. And so if you can see that there, follow the line down there, you'll see that the trough actually bottoms out a couple days later in the Z-band here. Now doing it by eye is a lot of fun, but computers are usually better at this kind of thing. So we use 3 different programs to do it, and I'll cover that in a second, exactly how those work. But once you've gone ahead and measured your time lags, assume that we've done that already, we then go ahead and plot time lag versus wavelength here. So the x-axis here is the wavelength of our filters, with each point here being the central wavelength of each filter. The y-axis here is the time lag in days we're observing it. Our G-band, since that's the reference one, that's one we use to compare to the others, that one's always going to be 0, okay? And so what we want to see is that as you go up in wavelength, you should go up in lag as well. And the inverse should also be true, where if you go down in wavelength, it should go negative in lag. So you can see here, if you go up, it seems like NGC 7469 is doing good. But if you go down, we would expect the U-band lag to be negative, and right now it's more consistent with 0. So that's a bit of an interesting feature there. And so we want to see, though, mostly if it fits this lambda to the 4/3 model. And so we actually fit a modified power law. This is the actual equation we use that we fit to it. And the reason I'm showing you this is mostly to highlight this parameter here. This is the normalization constant tau naught, and it's sort of a proxy for the disk size. So instead of actually going and measuring the disk size, we get these tau naught parameters from the fitting. And as you have a larger disk, you're going to have longer lags, and thus you will have a bigger normalization constant. So it's not a direct measurement of the disk size, but it's good enough for the sake of doing size comparisons between AGN. So let's go ahead then and show you some of the biggest study. Oh, let me show you first the way we measure time lags real quick. And so I use 3 different methods. The first is the cross-correlation function. I use specifically a program called PyCCF. And in case you never used a cross-correlation function before, I'm sure many of you probably haven't, it essentially shifts the time lag, or the light curves with respect to each other, and measures a cross-correlation coefficient at every step. This is actually NGC 7469's cross-correlation function when I do it between the G and I band. And so you can see it forms this nice sort of peak structure. And this is how we actually determine the time delay between our 2 light curves, is by finding the centroid of this cross-correlation function. Then another method we use is called Javelin. So Javelin assumes an underlying variability model of dampened random walk, right? Essentially saying that on shorter time scales, it's free to kind of wiggle and walk as it wants to, but on longer time scales, there's a fixed variability amplitude. And so this is great because it allows us to actually get through, get lag measurements when there's a lot of breaks and observations, right? So say bad weather happens, something yada yada, we can actually simulate what the light curve looks like. So the top here is actual observations of an AGN. The bottom here is the simulated in gray of what it would look like, right? And so it uses the real data to try and find a driving light curve and measure the lags with respect to that. You can usually get a lot smaller uncertainties that way, but you are assuming a model, so that sort of, can be a little tricky sometimes. Finally, we also have Pyroa, which also makes a model of the driving light curve, but uses a running optimal average instead. So essentially, it will just follow along your data and take X points left of it, X points to the right of it, and make an average. And this creates a sort of smoothed out version, which is the red version of the blue data here. And so what it'll do is try and make a driving light curve out of that and use that to find the light curve, time length. Okay, so we've gone ahead and talked about everything we need now to do an actual reverberation mapping study. I can't wait to see your papers when you're done. But anyway, what we have here is some results from some previous campaigns that have been done. Each data point here is one filtered with observations, and for these studies, they use some space-based observatories. Don't worry about the color or shape of these points, just know that each one has a filter that was used to sort of observe these AGN. And we have 3 here, NGC 5548, NGC 4593, and Markarian 142. So if you look at this black line, that is that lambda to the 4/3 model that I was describing earlier, right? And so just, in general, the lags do follow that black line. But I can see many of you already looking and thinking, oh, Jake, look at all these points where it goes off. And that's what I'm going to talk about next. So right here is the X-ray region, right? This is actually a sticking point where a lot of the X-rays that we're observing don't seem to correlate well with the UV and optical, which is sort of a big problem. If you were paying attention when I was speaking 10 minutes ago, it was about like the X-ray should be driving that variability, right? And right now they're completely off. Yes, question.
Yeah, so I wanted to, maybe you're about to say this, but the mechanism by which the X-rays drive changes in luminosity.
Mm-hmm.
So is it the X-ray is heating the?
Yeah, it's reprocessing. Essentially, it is sending these X-rays into the disk, it's heating them, and then it emits it out as a different wavelength of light depending on the disk's temperature itself.
So the thing that gets me a little confused. So suppose you have a big flare, so there's like a lot of X-rays on the disk. So then the X-rays would be heating up the disk a lot, and as you said, the disk has different initial temperatures.
Yes.
But then, as you have more heating, then the temperature of the disk is changing. That increases luminosity, but that also will be shifting the band in which you're seeing the emission from the different parts of the disk, right?
Yes. So with any band we're looking at, it's not exactly one region of the disk that is producing that light that we're observing. There's a range of it. And so you're entirely correct that it would be shifting potentially a little bit the region that we're observing here. But in general, it shouldn't be shifting it by too far to the point that we're seeing different regions of the disk. Does that make sense?
So let's see. So the emission that comes from, I don't want to hijack you.
Sure. We could talk afterwards. Or
yeah, so it's just like the amount, it's black body emission, right?
Yeah.
That goes as temperature to the 4th
Yeah.
power. Mm-hmm. The wavelength shift is by the temperature.
Right. Sure. But yes, anyways, the X-rays don't really correlate well with what we're observing, right? We 100% believe that they should be, but they're not. And so that's a question that a lot of current studies are trying to answer is what is actually driving the UV and optical variability? Because the UV and optical are very well correlated with each other. They're following along each other fine, but it's the X-rays that don't. So Markarian 142 and NGC 4593 here have very large disconnects, whereas even for NGC 5548, where it does seem to agree, there is as large, the correlation between them is much worse. So that's just a problem that is being addressed in many studies today, or is trying to be. The second is actually the normalization parameter. So you may remember this equation I showed you earlier, and specifically this parameter tau naught. We can actually calculate this value based on things like the mass and the luminosity that we're observing for this AGN. And so when we actually calculate this value, we get these dotted, or these dashed black points here. And so these are the predicted values, and this is the observed value. And typically there's like a 3 times offset, meaning that the disks that we're observing are 3 times bigger than the disks that are predicted. And so this is very confusing, right? People have been trying to figure out what's going on here for a while now. And there's still not an entirely good answer because some AGN agree with the predicted values. So it's sort of a question of why do some agree? Why do some not? What is driving these AGN to be different? And then finally, the third problem I'll talk about today is the U-band excess. This is a region of the wavelength around 3,500 angstroms, where we see that's where the U-band is located, where it kind of probes. You can see these large excesses in the lags here. Specifically in NGC 4593, it's very prominent, and you can see that it is variability beyond that lambda to the 4/3 model. So we have these 3 problems and a lot of questions still to answer, right? We got to try and figure out exactly what's going on in the story here. And that's sort of where my research focuses. Mostly on the bottom 2, because I work with ground-based robotic observatories and the optical. So I don't really have much X-ray probing. But when it comes to the optical stuff, that's what I am trying to figure out. So I want to highlight the broad line region, right? This is a region that is just outside the accretion disk and is this sort of groups of clumpy clouds that emit both emission lines, right? This is where your H alpha comes from and whatnot, but also continuum emission. So the continuum emission is produced by bound-down and bound-free electron interactions, and we think it looks something kind of like this. This is just a simulated model of the broadline region luminosity. And so you can see here, this is the x-axis for wavelength, y-axis here is the luminosity strength. It has sort of a weird shape here due to these different jumps, but essentially this is producing a bunch of variable continuum emission at potentially similar strengths to what the disk is producing. And so if that's the case, that could explain and has often been invoked for why the U-band excess exists, because we're seeing this large increase in luminosity from a source that's much farther out. Here's my little diagram again, is the broadline region here, right? It's further away, producing very similar emission. And again, because these things are so compact, we can't disentangle just inherently the disk versus the broadline region emission. So if we want to try and figure out more about the broadline region influencing our results, we need to get, again, a bit more creative and analyze variability patterns as opposed to just light itself. So I'll talk a little bit about Markarian 876. This is the first study I ever did as a graduate student, looking into an AGN known as Markarian 876. We looked at it with 3 different telescopes: Liverpool, Las Cruces Observatory, and Watt Observatory, which is from my old university. That's their remote robotic observatory. This is an image from it, and this is Markarian 876 located right here. The light curves we have for each band are right here, U, G, R, I, and Z, similar to what I showed you before. And you can see that we have these cross-correlation functions for each band on the right here. Now, these ones look a lot different than the ones I showed you previously. These ones are a lot broader. They're like plateaus, right? They go right up, and then they hang out for a while, and they go back down. And these are also much broader than what we saw before. So what we're seeing here is that due to how long the light curves we're having, we're actually catching these long-term trends in the AGN light curve. We're seeing how these long-term trends are dominating our cross-correlation signal. And this is not the signal we expect from X-ray processing. This is way too long of a time scale. So what we do here is we detrend our data, right? This is something that's pretty common when it comes to CCF studies, but it's important to talk about because everyone does it differently. So the way that we do it is that we use a moving boxcar average and subtract off that average from our original light curves to get our detrended light curves. In theory, this should remove that long-term signal that's sort of dominating our variability patterns. And when we do that, we do find much more reasonable cross-correlation functions. You can see here, this looks way more like what I showed you previously than these guys do. And so we use a moving boxcar average of about 100 days. For those of you that aren't familiar with a moving boxcar average, it's sort of like it goes along your data, takes the average from X points left and right of it, and then we then subtract off that average to get our detrended light curves. So something that we just need to mention, that we do that and we use detrended light curves going forward with our analysis. So with that analysis, we do our time lag results. We have PyCCF, which is the cross-correlation function I showed you before. We also have Javelin and Pyroa. And so you can see they all pretty much agree with each other. We don't see a U-band excess in our light curves here, which is interesting. This black line is that lambda to the 4/3 model I showed you before. But what we do find that's interesting here is an I-band excess, right? Which we didn't expect to see going into this. This is sort of like just a random jump in our data. So we wanted to try and figure out what was going on with it. So we took some spectra of it at both the beginning and end of our campaign. This dotted line here is the wavelength range probed by our I-band filter. And so the black is the data and the red is our model of a power law and a Gaussian. And we found that H alpha was dead center in the middle of our filter, right? Which would make sense given its redshift. But we found that it was contributing about 30% of our total signal. With this in mind, we looked at some archival studies of the H alpha time lags and found that it had a lag of about 40 days. This means that it was essentially contributing to that enhanced I-band lag we saw previously. And so this is sort of showcasing 3 different scales of variability in Markarian 876. We have the X-ray reprocessing, we have the H alpha varying on timescales of about 40 days. And this is important to note, would not be removed entirely by our detrending processes. We only look for longer term timescales of that detrending. With this, we only have the 40 days, and that allows it to kind of sneak in, if that makes sense. And then finally, we do have that long-term variability as well. And so I don't have time to go over all the analysis we did in this paper. So if you're interested in it, here's a QR code here. I'll also put it at the end of the talk too, in case you're interested. But this is sort of just warming you up to how AGN analysis kind of works. I'll now go over the 4 years of observation that we did with the Watt telescope exclusively. And so what we did is looked at 18 unique AGN consisting of a total of 25 sets of light curves, essentially trying to build up a population study of these time lags, right? Some others were repeated over multiple seasons, so that's why the numbers don't match exactly. We then measure the time lags of each object and determine the disk sizes, find those tau naught parameters for our entire sample, okay? And then once you've done that, we then combine that data with other studies to see if the variability patterns in these AGN agree more with the accretion disk or what the broadline region has been seen to produce. So here's a couple of objects we looked at, and here's a couple of light curves taken from the Zawada Observatory, just to sort of highlight what it's capable of, since not many people know about it, but you can see we get some pretty high quality light curves, which then leads to pretty high quality time lapse. So to determine the difference between disk-dominated variability versus broadline region-dominated variability, we need to look at the theory for both and compare them. So breaking down the theories a little bit, we have for a disk, we expect the tau naught to be roughly proportional to mass times luminosity to the 1/3 power. And this comes from Shakir-Needed equations as parameterized by Thousand 2016. For the broadline region, we instead expect it to be just proportional to luminosity to the 1/2 power. This has actually been observed pretty frequently when it comes to broadline region studies. And so what we want to do is try and directly compare these two against each other and see if our disk sizes agree with one or the other. We just plot disk size versus luminosity and see which pattern it follows. But the problem is we can't just directly compare them because of this mass term located in the disk version. So what we want to do is find a relationship between luminosity and mass to remove that mass term, which we do. We essentially combine all of our studies together, the stuff that we did with a couple other survey studies to really fill out the population. And we just plot mass versus luminosity and fit a power law to it to see what the relationship is empirically. So we find a relationship between luminosity and mass of 1.23, which we then plug back into our equation and get a new relationship for the disk just in terms of luminosity. That is tau naught is proportional to L to the 0.6. So just to highlight that, here are the two again, but just a little bit simpler. So it's either 0.6 if it agrees with the disk, or 0.5 if it seems to agree more with the PLR. Now that we've done that sort of footwork, we can now see, we plot tau naught versus luminosity to see if either scenario is preferred. Here it is. Oh, there we go. Okay, so what we do here is we just plot our highest quality data set on the left here versus the entire data set on the right here and fit a power law to both. And so what we're seeing here is that the BLR interpretation appears to be preferred, which is actually in line with similar studies of less data points. We find here that depending on either with both of these in mind, the BLR interpretation appears to be coming out as a bit more preferred, although the relationship, the exact amount is pretty close, right? So it's going to be hard to tell the difference, especially with the scatter already, but we're finding here that it does seem to be slightly preferred. And this is, again, in line with what, for example, Guo et al. Found with his data set alone. We sort of expanded down to this lower region here, but we're finding the BLR interpretation is still preferred. But there's still a lot of work to be done, right? This is not the end of the story, not by a long shot. But just as a brief overall conclusion of what my work is sort of focused around, it's that the broadline region appears to be influencing our results with continuum reverberation mapping pretty significantly, both through emission lines that it's emitting and also from that continuum emission it's been doing. We saw it with both Mercurian 876 in the form of the H alpha emission. And then from this analysis looking at the disk sizes, we're seeing that the BLR dominated variability patterns seem to be more present than the disk dominated. Then, however, though, as I was saying before, there needs to be more studies done. And so this is actually an older plot of mine that I dug up for this talk specifically. This is NGC 4395, and this is a intermediate mass AGN that I tried to put in our data point, but it was so off the map that we had to remove it because it was completely dominating the fit. This is an intermediate mass AGN that lies so far off of it that we just can't use it. And so we need to fill in this region here. And that's sort of what I want to do here at Texas A&M, is try and find more of these AGN, add it onto here, and figure out if we can learn anything from them. So without any further ado, that's sort of the end of my talk. I'd be happy to take any questions. Yeah.
Have you explored differences in Seifert type?
We normally only use Seifert 1, just because,
Okay.
yeah. Mm-hmm. So no, I guess would be a good way to put it.
Airline Seifert ones? Or very?
That one we haven't been controlling for, so that could be something we look into. But
changing look one.
Sure, changing look ones, yeah, 100% could mess with that. But the ones we chose and only have ones that only have masses that have been found with reverberation mapping, at least the ones that I picked for my studies. So that one hasn't really come up that much, but that's a good question. Yeah.
I have two questions. One is about the sample. So you
Okay.
mentioned like the 18 unique AGNs.
Yeah.
Them.
We chose them initially based on just the availability to be observed with the Zawada Observatory, which is only a 0.5 meter telescope. So typically the closest and brightest ones that we could find, and also ones that had a reverberation maps from like DLR analysis have been done
Do
previously.
you have any plan to make it like a complete sample?
Oh, yeah, and that's what I want to do. But the problem is that we don't have that. I didn't have access to that stuff back at Wayne State, essentially. Mhm.
And then the UV access, I know the some AGNs, probably the most of AGNs have this, like a subparsec scale, have this ring structure, like a ring of stars, ring of young stars.
Mhm.
And I was wondering whether these stars actually like contribute this UV access, because we know that these young stars are dominant in the UV region.
You know, that's a great question. Actually, someone I worked with back at Wayne State studied the soft access explicitly, and they thought it was due to this sort of a soft corona as opposed to the hard corona. That's another potential reason, though. The ring of young stars could potentially be it as well. That's sort of outside of my wheelhouse a little bit because I mostly work with optical stuff. But just to sort of, yeah, that soft access could be from that or potentially corona shenanigans. It's too soon to say. Mhm. All right. Thank you all so much.
Okay, let's switch speakers.
You want to use the clicker?
Sure,
Yeah.
thank you.
Yeah, I don't know if you have a little USB C slot for that one.
Okay.
Okay.
Okay. Let me use this one.
Is per pixel.
There's
no
button here.
Oh, because it has to do that. Yeah, I tried to go.
Should.
Right, so I moved this file.
Okay. So it is good. Okay,
And then you have a USB. For this,
for this.
yes.
Okay, I don't have a USB.
Okay, so we can-
Yeah, okay. Well, thank you and thank you.
All right. Talk two is from Park Zheng, who was a grad student at Ohio State and now a new postdoc.
Thank you for the introduction, so I have to give that part. So, good afternoon, everyone. I'm a news postdoc here, so I guess I'll see you around for the next 3 years or so. Yeah, so my topic today and in general, my research projects are mainly focused on dark matter related simulation. In particular, a type of it called the self-interacting dark matter and the substructures produced by them. Okay. The keyword in this kind of study, or the talk today is the diversity produced in the substructures. And these are my awesome collaborators. Okay. So first of all, some background introduction on the motivation of why we want to look into or investigate into these weird type of dark matter models. That's because in the past decade or so, people have come to discover or actually realize that there's the so-called diversity problem in dwarf galaxies that are observed. So that is to say, they observed properties of dwarf galaxies. They display a larger scatter or diversity than the expectations from cold-dark matter, where cold-dark matter is generally considered the standard model of modern cosmology for dark matter. These properties that display diversity include something like the standard thing that you look into a galaxy, things like rotational curves, things like the mass-size relation, etc. So here I show some demonstration of the so-called diversity problem. In the left panel, we have
the x-axis being the maximum circular velocity of certain of these dwarf galaxies in either simulation or observation. In y-axis, we have the circular velocity at a certain fixed aperture, which is a pretty inner small radii. So these two can be considered proxies for the total mass in the x-axis and inner mass in the y-axis. So we have 4 panels here. The gray panel or the top left panel refers to the dark matter only simulations. The red data points refers to the dark matter plus baryon simulation, so the full hydrodynamic simulations. And the blue data points here are actual observed dwarf galaxies. So you can already see that they display a much larger scatter than even dark matter only plus full hydro simulation combined together. Okay. In the red panel, we have in another format, but pretty much a similar thing. They pull up the rotation curve directly. So the colorful lines are the outlier dwarf galaxies that are not easily fit into the representative ones from CDM based. So you can see there's a larger scatter easily in observations. This is still a diversity problem in 2 different but related aspects. The first one is the derived dark matter halo inner density slope. The black data points are from Milky Way dwarf spheroidals, and the 2 colorful bands are results from 2 state-of-art hydro simulations. You can see even if they span large range, they cannot fully cover the region from Milky Way observations. Okay. And the last panel here is the mass size relation. Mass size refers to the stellar mass and stellar size of the observed dwarf galaxies in the black dots here, and the blue dots are the similar things but found in simulations. So still, the simulation results in blue spans a much narrower range than the observations. So that's a few aspects to look into the so-called modern version of diversity problem in dwarf galaxies. So that's about the diversity problem. So why are people looking into? So from the total mass versus inner mass panel, you can probably guess there might be something interesting going on in the very inner region of the dark matter halo. So that motivates people to look into alternative dark matter models, of which SIDM is one of them. Why is that? Because SIDM is basically on top of cold dark matter, which is gravity only. People ask this question: what if there's some efficient particle scattering? What would happen to the halo if there's such additional self-interaction? So the short answer is that if you allow for self-interaction among particles, effectively you're allowing for efficient heat transfer among different shells of a dark halo. And eventually that will lead to this unique 2-phase evolution in an SIDM halo. That's first you'll form a density core in the center, and later on, after a long time of evolution, the core will eventually collapse to be a very cuspy profile. So let me try to illustrate this. So for example, you start from a typical CDM halo in the orange color. The top panel is a density profile. The density is a function of radius. And the bottom panel is a velocity dispersion profile, or in other words, a temperature profile. So velocity dispersion as a function of radius, which peaks somewhere in the middle. So that's also a temperature peak. When you turn on the self-interaction, which means you allow for heat transfer among different shells, because this is a temperature peak, naturally you will expect both heat inflow and heat outflow. The heat inflow will soon lead to the core formation and thermalization in the inner part, because the density is higher in the center. So the scattering rate is also higher. So the thermalization happens fast at first. So you go from the orange line to the blue line in both panels. Okay, a core formation in both panels. But there's also the heat outflow, which is relatively slower because the density is lower. So the scattering rate is lower, the heat transfer rate is lower. But it is also an endless process, because the inner part, the blue, now we're on the blue stage. It's hotter, it's always hotter than the outer part. It can never thermalize with the outer part, because the heat transfer to the outer part can lead to particles or dark matter become unbound from the system. The inner part is always a heat reservoir. So after a long time of evolution, what happens is that the inner part loses heat, it transfers heat to the outer part, where the matter will not be able to stay at this higher orbit. It has to contract to a closer orbit where it becomes even hotter than before because the gravitational potential energy is transferred to kinetic energy. So it gains more energy, it becomes hotter in the center where it accelerates this process because the temperature gradient gets higher and higher, means getting more and more negative. So it boosts the efficiency of such heat outflow and matter inflow. So eventually, this process, as I said, is self-accelerating and will eventually be a runaway process that will lead to you go from the blue quartz profile to be a very cuspy green profile in both. So that's a core formation to core collapse. If you start from orange profile, that's typical for CDM. You have core formation going to blue, and eventually you collapse into green. Okay. So already you can expect a larger, much larger scatter than CDM in the inner part because of the such two-phase evolution. The inner density already spans for like 3 orders of magnitude or so. Okay. So this is a simple animation of the previously mentioned process. So the black line is CDM. It's a dark matter halo profile, and the purple lines are from a specific SIDM model. So you can see first it quickly drops to form a core, and after a long time of evolution, it becomes cuspier and more denser and denser to make a core collapse process. It's slow, it takes a long time, but you can also notice they say the late time accelerations. It's self-accelerating. So just to demonstrate the process. Okay, so again, from this two-phase evolution, you can already see the inner density, which is hopefully what exactly causes the diversity problem that spans the weather range during its whole life cycle. So that's what people mean by SIDM can potentially resolve the diversity, because you can, when you look at a halo, you may be looking at it at different life stages during its whole life cycle. Right? It may be at core stage, it may be at core collapse stage. So key features of the core collapse happening is the center gets denser, the center gets hotter, and the density slope here gets steeper and steeper, so more and more negative. Okay, so that's all for background. So time to show some actual results. So here, what I'm showing here is the biggest panel. We're showing the time evolution in axis of 4 individual SIDM subhalos with different parameters, but that doesn't matter. Okay, so the y-axis is the central density. That serves 2 purposes. First, as the main tracer of the core collapse process. Second, as the main quantity to demonstrate the level of diversity that it produces. Okay, so for example, if we look at the simplest case, the thick green line here, it starts from a CDM central density. It quickly drops by over an order of magnitude due to the core creation phase. Okay. And then core collapses, where the central density raises up again, raises by about 2 orders of magnitude, at least, because we terminate the simulation here, because we have to. At least a 2 order of magnitude gain in terms of central density compared to CDM. So you can already see a 3 orders of magnitude span in terms of central density. That's the simplest case. There are 3 other companions that also tries to follow the same process. You can see they tries to rise up again, but somehow they get disrupted together at the pericenter. So the second panel shows the orbital distance of the subhalos to the host halo center. And after the first disruption, some of them have a second chance to manage to core collapse again, only at a later time, with periodic ups and downs, again, strongly correlated with the pericenter. Some of them, like this poor guy, they never get a chance to rise up again in the central density. So we try to understand, first of all, it introduces even more diversity to the process because we can see these weird ups and downs periodic. And second, we want to understand why does this happen? Obviously, that's orbital effect because it has strong correlation with orbital history. But okay, let me skip a lot of details in between. So the conclusion here is we disentangle the relevant physics processes into mainly 3 terms. 2 of them are heating terms in red, and one is a cooling term. These terms altogether drive the growth or evolution in the central density of the subhalo. So the cooling term is actually the intrinsic heat outflow from the center, because it's outflow, so it's cooling in the center, transfers heat out. Right? When it cools down, it contracts and causes the central density to grow up. Okay, so there are also 2 other heating terms that is not intrinsic in the subhalo itself. It's highly related to the orbital effect. First is the evaporation, which is basically the self-interaction effect between a subhalo and its host halo. That is to say, okay, you have a pair of particles scattering off each other, one coming from the subhalo, one coming from the host halo. They have vastly different velocities. So when the scattering happens, the velocities get redistributed because they scatter off each other. Because the income velocity is very different, so the outcome velocity is in the center of mass frame of the subhalo. It gains the scattered subhalo particle will gain a lot of velocities, will eventually lead the particle to become unbound from the subhalo. So that is to say, the evaporation process will cause extra mass loss on the subhalo. That is happening at all radii of the subhalo. Okay. The tidal heating is basically the tidal force. When the tidal force is strong enough, it strips away particles, materials from outliers from the subhalo. When it's not strong enough to unbound particles, it still does positive work to the system. So because it's positive work, so it's a heating term. It pumps up dark matter in the center. So these 2 heating terms, because they're all heating terms, they cause the center to puff up a little bit, maybe more than a little bit. So eventually disrupts the core collapse efforts, which is dark matter want to concentrate at the center. So overall, this is to say, okay, when coupled with orbital effect, we have even more diversity in the evolution history of subhalos. So that's for dark matter only studies. Now the actual question we need to look into the diversity problem is, to what extent is this diversity in dark matter only content? How it's gonna be propagated to the observables in stellar components. Okay. To do this, we come up with a new simulation with 2 species of particles. One is dark matter, where we have both gravity and self-interaction. One is stellar particles, where you only have gravity. The idea is to see, okay, we have dark matter going from core formation to core collapse and orbital effects. How does the stellar particles respond to such complicated processes? And what kind of diversity can it produce? So these are all preliminary results unpublished, so don't tell WikiLeaks. Yes. So we have 4 panels here. Each one represents a dark matter model. The first one is a vanilla CDM model. All right, this is a basic slide. So and the isolated dwarf galaxy. So this is all panels are showing the time evolution in x-axis of the time evolution of the half-life radius of the corresponding dwarf galaxies, either in isolation in the solid lines or the orbiting cases in different other line types, the satellite galaxies. So we notice a couple of things here. For the isolated cases, we notice first a universal procreation stage or formation stage, where in correspondence to the formation of the dark matter halo, the stellar component, they diffuse out by about 50% in galaxy size. You can see this red solid line, this pink solid line, and also this purple solid line. About the same amount of 50% increase in galaxy size. Only that this model, this dwarf galaxy successfully core collapses at the later time. That causes this late time sharp drop in the galaxy size, because when the dark matter quickly concentrates to the center, the potential gets sharply deeper, and also it drags the stellar particles toward the center in a fast manner. Another thing is a temporary size boost caused by the previously mentioned evaporation effect, because we lose a lot of dark matter suddenly in the center. The potential gets smoothed out, and the stellar particles just freely cored out as well. So that causes an increase in the galaxy size. And the last point to notice for specific reason is the formation of these dark matter free galaxies, which is also in correspondence with recent discoveries. The formation of such galaxies are very efficient when you have efficient dark matter loss in SIDM models. So that one was time evolution of the stellar properties. Now we're correlating them not with time, but with the evolution of the inner mass, which we believe to be what is driving the stellar properties. So this serves the purpose for future studies. The idea is like this. Okay, the y-axis being the galaxy size, the x-axis being the inner mass within the dwarf galaxy. Inner mass meaning stellar mass plus dark matter mass. The idea is the y-axis is what we care about in observations, but it demands ultra high resolution to actually study for high fidelity. The x-axis we cannot actually observe, but they may be less demanding in terms of resolution in future simulations. So we can easily reproduce them. Okay. So the idea is, okay, y-axis is difficult to simulate. What if we can build a relation between these two? If we can find a parameterizable form and we can roll such parameterization into future low resolution simulations, we can reconstruct or predict the stellar properties given different SIDM models. That's the so-called tidal track study. So let's look into this. So each line represents a dwarf galaxy. They all start from the same initial condition, the red dot here. Following the previously mentioned processes, the rightmost line is a case in isolation, where starting from the initial conditions, you first have the core creation phase, where the galaxy size increases because of the core out effect, and also the inner mass decreases, so it moves towards the top left corner, and the core collapse stage is just taking a U-turn back down. Okay, so this is going this way and then back down that way. And the subhalos, because they yield to different levels of inner mass loss, they are aligned towards the left direction. And the subhalos that eventually remain core or successfully core collapsed, they fall onto different two branches, the green for the core branch and the cyan ones for the core collapsed branch. And these two branches are very distinct from each other. So this is to say this plot is, they look messy, but they are highly explainable and does have the potential of being parameterized in the future, although there are still much effort to be done on this front. Okay. So two key points from this figure. First is diversity. Diversity means the evolution of the stellar properties. In this example, the galaxy size, they does span a large portion in the parameter space compared to the CDM model, which is the little black guy. Okay. The second point is the universality. You have to put a pattern mark here that I just mentioned, is that the potential of this kind of relations being parameterized into nice functional forms for future use. Okay, finally, last figure. So similar things, the tidal tracks, but not in terms of the dark matter model, dark matter physics. This is showing the evolution tracks of SIDM dwarf satellites in terms of the stellar mass to stellar size plane. So the y-axis being the galaxy size and the x-axis being the stellar mass. So, and we're overlapping it with a few observational results. So we can see the amount of the scatter or the span. Even if we only use one initial condition, one specific initial condition, it does cover a whole lot of the observational space. Seems like it's a pretty promising thing to explain the observed large scatter in dwarf mass size plane. It's just very preliminary first peek into the problem. So that's pretty much everything. I'll stop on the takeaway messages and I'm happy to take questions. Yeah, go ahead.
So, okay, so the core formation and core collapse cycle that occurs in both the overall halo in which the large galaxy lives and the subhalos that form off of it?
In principle, yes, but we don't want that to happen in the big halos because they're easily ruled out.
Okay, so that was what I was gonna ask, is like, if this is true of the large halos also, is there something about the big galaxy that could,
Yes.
like, the population of big galaxies that would
Right.
tell you that that's not happening?
Yes, so that means we can rule out a large portion of the SIDM parameter space
I see.
by that.
So in practice, you've just like dialed the parameters so that the core collapse only happens.
Yeah, that's been,
Yeah, that's fine. Worst things have been done.
And I had another.
yeah, sure.
So you mentioned that in some, like, one observable consequence might be a population of dark matter free or dark matter deficient galaxies. I mean, I don't study dwarfs a lot, but I thought that we were actually finding like a lot of really high mass to light ratio galaxies, like the
They're
ultra.
both in.
Oh, okay.
Part of them are dark matter, nearly completely dark matter free. Some of them are nearly completely dark matter dominated. We find also there are very recent discoveries. We find extremes on both sides. So that's why we are looking to SIDM for even more motivation because they're too extreme.
Thanks.
That's a question. So like, there's no universal mass profile for SIDM anymore, right? Like, there's no universal, like for NFW. There's no like,
Right, that's actually a great question. If we can parameterize that, maybe throw in a function of like with a additional parameter of time parameter or something.
yeah,
If that's doable, then that's good news for people modeling that.
I mean, if you waited to even just like asymptotically long, right?
Right, I mean, for isolated cases, people find universal evolution with proper parameterization, but with various orbital effects, we haven't found that yet. It's still to be studied.
I just realized that actually.
It's really difficult. Any more questions?
More questions? Let's thank both our speakers.
I think so. But
Yeah.
what about the, like, do the ultra faint ones?
Oh, those are the dark matter.
Right.
dominant.
Yeah, please.
Or does this explain both ultra diffuse dwarfs and ultra faint?
Okay, no, that's fantastic.
Of these things, some of them
Luminax.
become dark